All right, we're back. We're still on page 2 of Calc D Notes 1, doing some background information on vectors, making sure everybody's up to speed. This should all basically be review, and if it's not review, go back and watch the math analysis videos or do the math analysis notes. Make sure that you are ready to go with this. So that's why math analysis is really a pre-calculus course. It's pre-calc 1, 2, and 3. So some of the stuff you do, you don't get to until Calc 3. So if you never take Calc 3, feels like a waste of time, but here we are, and it's all useful now. So let's see. Finding the terminal or initial point of a vector is something we might need to do. It's definitely something we probably need to do. So let's try to find the terminal point of this vector if the initial point is this. All right, so this kind of just comes down to what vectors are. So if we have an initial point here, let's say it's A, and then let's say we have a terminal point here, then this would be our vector v. So what I want to do is I want to start at the initial point, and then I need to go 3 in the x direction, -2 in the y direction, and 7 in the z direction. So I can actually find my terminal point by doing one, I need to add 3, I'm starting at -2 and I need to subtract 2, and then I'm starting at 8 and I need to add 7. So my terminal point should be 4, -4, 15. Okay, so what's another way of doing that? Another way of doing that a little more mathematically is to say that let's let x, y, z be the terminal point. Then I know that x minus 1, y plus 2, z minus 8. So I just found the difference. I did like terminal minus initial, right? So it's x minus 1, y minus -2, z minus 8 should be equal to that given vector, which was 3, -2, 7. 3, -2, 7? Yeah. 7. Yeah, okay. And then you can see like x minus 1 is equal to 3. Let me do some highlighting. X minus 1 equals 3. Y plus 2 equals -2. And then z minus 8 should be 7. And then you can see from there that you're going to get x is 4, y is going to be -4, and then z will be 15. So that's like a little more mathematical if you prefer. And you can always do this. Like this is a very effective means of doing that problem. So here we want to go backwards. So find the initial point of the given vector. That's not a highlight. That's not my laser pointer of this vector given the terminal point, right? So I think the easiest way to do this, right? We want to find the initial point. Here's our terminal point. So this is the point that we know, right? This is 5, 0, -1. And we want to find this point. So from A to B would be V, which means that to go from B back to A, we would just use -V. So if I consider this the initial point of the vector -V, I can find that as the terminal point of -V, which must have been the initial point of vector V. So it's like using the opposite of a vector is like reversing time or going home like from your trip. So that would tell me that the initial point, and then I'll do it like more mathy. My initial point should be, if this is kind of my initial point of my return journey is 5, and then I have to go 3 to the right, so it's going to be 8. And then my initial y value on the return journey is 0, and I have to go 1 to the left to undo that, so that'll be -1. Then I'm at -1, and I want to go home, so I have to subtract 2, so -3. Okay, so that's like I think that's a mathematical way of doing it, but you might not like it so much. So if we do the whole thing like x, y, z be the initial point, well, we got to do terminal minus initial, right? So it's going to be 5 minus x, y minus 0, z minus, nope, sorry, because we're going that's the initial point. So it's terminal minus initial, 0 minus y, -1 minus z should be the given vector, -3, 1, 2. -3, 1, 2. So from this, again, we get our equation. So x is definitely 8, and then here, y is definitely -1, and then here, that's a 2. So if I don't cross it, it's a 2, because my 2's and z's look really similar, but you can see that z would be -3 if we solve that. Okay, so that's how we can do it. This is the mathematical way, or the, like, I don't know, like the super algebraic way, where you don't have to like have the insight. I think having the insight is better. Like thinking that through, I think, is a better idea, but you know, whatever. All right, let's find some dot products. So dot product feels like you're multiplying, but multiplying vectors doesn't really exist. So what we do is component by component multiplication, and then you add. What is a good way to say that? You multiply corresponding components and find it's the sum of the product of corresponding components. That's what it is. The sum of the products of corresponding components. So if I want to do a dot b, what I'm going to do is this times this plus this times this plus, I don't know, this times this. Okay, so it's going to be 1 times 6 plus 1 times 4 plus 1 times 2. Using 1, 1, 1 is like really obnoxious because, you know, you could be totally doing it wrong and get it right. So 12, what do I know? I know since a dot b is greater than 0, the angle between a and b is acute. That's one of the things that I know because of that. So, you know, that's just something to keep in mind. We're not really talking about it yet, but we should be. All right, let's see what this is. Why are these in parentheses? I don't know, some artifact of ancient typing that I did. So I'm going to rewrite these because I hate using IJK form. So this is 1, 1, 1, 1, 1, 1 again. Interesting. Why did I do that? 3, 2, -5. Oh, I can see what's going to happen here. All right, so we're doing the thing, right? It's corresponding components, we multiply them, and then we sum up what we get. So v dot w, UVW are like the most common things for vectors. Plus 1 times 2 plus 1 times -5. We add these up, we get 0. Very interesting result. That's the most, in my opinion, the most interesting dot product you can get. If you get that as your dot product, so since v dot w equals 0, v and w are orthogonal, which means the angle, so theta is pi over 2. The angle between them is pi over 2. That's a huge result. That might be the biggest result you get from dot products. All right, do I want to do any of this on the calculator? I guess so. I mean, like, let's go to the calculator and take a look. I'm not going to do anything on GeoGebra with this because I don't think, I mean, I guess like the interesting thing is I could plot the vectors and actually see that they're orthogonal, but I'm not going to do it. All right, new problem, new problem. All right, so let's say that we were doing this previous one. So I'm doing find terminal point of, so v is going to be 3, -2, 7. The initial point, which I'm going to call a, is 1, 2, -2, 8. Okay, and then b, the terminal point, I'm going to say is x, y, z. So let's just solve that. 3, solve b minus a equals v. Solve that for x. Well, we can just put x. So 4, -4, and 15. There you go. I mean, couldn't be more straightforward. -3, 1, 2. B is 5, 0, -1. A is going to be x, y, z. And let's solve it. Solve b minus a equals v for x. So So we get 8, -1, and -3. So we got it. Nice. Dot products. So we can definitely do dot products. So A is a vector 1, 1, 1. B is the vector 6, 4, 2. Oh, that's what, yeah, I forgot to put it in a vector. There we go. Okay, now dot product, menu 7, C, option 3, menu 7, C3. Dot product A, comma, B. You have to give it 2 vectors. You don't need to store them ahead of time, but I do. And then, so I'll do the next menu 7, C3. I'll just type in the vectors 1, 1, 1, and 3. Oop, forgot again. 3, 2, -5. And we should get 0. And there we do. All right. So that's it. Again, use your calculator every chance you get, because the better you are at your calculator, the more problems you can solve, you know, and the more insights you can have. So let me see. All right, this is what we got, and that's page 2. And I will be back in the next video to do, I guess, probably page 3 if I had to guess. So I will see you there.